Hello and welcome to Q-Control's webinar series. So I'm Michael Hush. I'm the Chief Scientific Officer here at Q-Control, and I have with me today Chris.
I'm Christophe Valahu. I'm a postdoctoral researcher at the University of Sydney.
So welcome everyone. Today we're going to be talking about some work that we recently completed together with the University of Sydney, where we worked on characterizing one of their quantum devices, and in particular, a trapped ion. So as you're watching, at any point, you're welcome to ask questions. We request that you actually click that Q&A button. So there's a Q&A button in the Zoom profile down the bottom. Put your questions in there. That allows us to see them more easily and answer. Don't use the chat function. So the chat function is just there. I don't know why it's there actually. We can't turn it off. So, but use the Q&A whenever you want to ask a question, and you can do that at any point. And then at the end of the session, after we have a chat and we get past the presentation section, we'll be able to answer all of your questions. So yeah, it's great to have you here today, Chris. This is actually our first webinar. We've had someone outside of the company joining us. So thank you very much for coming along. Could you tell us a little bit about yourself and how you first found out about Q-Control?
Sure, yeah. So I recently finished my PhD about a year ago, a little over a year ago. I did that at Imperial College of London in conjunction with the University of Sussex. And that PhD was about robust entanglement gates. And that's when I first found out about Q-Control, where a lot of our work, we're trying to find optimal control solutions to get robust entanglement gates. And during that period, I got to use Boulder Opal. Yeah. And
I think we actually met at a conference in Australia around that time as well. Yeah.
Quite a few years ago, funnily enough.
Yeah, you're actually one of the earliest adopters. So it's good to get you as well.
Yeah. And then recently, I just joined the Quantum Control Laboratory at the University of Sydney. And so in this lab, we do various works around quantum control and chemical simulations, which we'll talk about after.
Yeah, actually, no, do you want to tell us a little bit more about that?
Oh, yeah,
if you'd like to, it'd be great to hear like what you're trying to do.
Yeah, of course. So our work at the moment is broadly based on two different things. The first one focuses on simulating chemical dynamics. Yeah. So we are a trap down lab, and in this lab, we currently have a Paul trap. And what we're trying to do with it is mimic a chemical dynamic simulation. So we take some molecular system and then we map it onto the trap ion, and we can map the external and internal degrees of freedom of the ion and make that basically one-to-one mapping with the molecular system. So that's work that we're very excited about mapping out now. But maybe what's more relevant and interesting today is our work on entanglement gates. Yeah. And so in this work, we have large chains of trap ions, and we're trying to entangle all of them. And we're trying to do this with a single step global process. So we have a global laser beam, and we try and entangle 5 to 10 ions in a single process. Yeah.
And so, yeah, when you were trying to achieve this, like this led to, I guess, our conversation about applying our control technique. So why was characterization a challenge in this process? And what will you be able to achieve once you can solve it?
So when we apply this global operation, there's various types of errors that arise from it. And these errors aren't particularly well understood. And as we scale to more ions, it's even harder to characterize these experimentally. So what we are looking for is a characterization solution that allows us to model, or that allows us to identify and measure and characterize these different types of errors, perhaps different correlations between different qubits, and find something that works efficiently and scalably. We also have a problem of flexibility on our hardware. As do every other experiment in the world have, we have various constraints. Now, our particular constraints are that we have a single global beam. And at the moment, at the time of speaking, we don't yet have single addressability. So a lot of characterization techniques will make use of single qubit gates, which we don't have. So we were in the need of a solution, a protocol, which takes into account the constraints of our system and allows some degree of flexibility. Yeah, great. So we're going to now hear a little bit more about basically the characterization techniques we applied together in your lab and how we work towards solving that problem. So I'm now going to just switch across to our presentation. Just share the screen.
Today's presentation will show you how to characterize your quantum computer faster and easier with automated system identification. Here at Q-CTRL, we create control solutions delivered through infrastructure software to research and development teams creating new quantum technology. We recently collaborated with the Quantum Control Laboratory at the University of Sydney in a demonstration where we characterize a trapped ion experiment 93 times more efficiently than what you can achieve with standard techniques. Characterization is the top pain point for most R&D teams. In a recent Q-CTRL survey of experimental teams, we found 50% of respondents ranked characterization at the top of their priority list. This is not surprising, as characterization can be expensive. Even simple tasks like characterizing an individual qubit can take at least 300 measurements with standard techniques. Furthermore, these techniques are hard to scale to multi-qubit devices and have to be repeated periodically as devices drift. This makes them costly in both time and resources. We also discovered that over 40% of experimentalists were unsatisfied with the current characterization routines they had in the lab. Standard approaches to characterization are often ad hoc, rarely optimal, and never automated. Fortunately, Q-CTRL's software solution Boulder Opal can solve your characterization needs. Boulder Opal is a Python module that can be directly integrated into your quantum computing testing and control setup. Boulder Opal is connected to our scalable cloud infrastructure to boost its numerical performance, getting you the right control solution faster. Aside from characterization, Boulder Opal can simulate quantum dynamics, design error-robust controls, automate hardware with AI, and verify performance. Whatever your quantum control needs are, Boulder Opal has the state-of-the-art tool to solve it. The focus of the presentation today is characterization. Boulder Opal has a suite of characterization tools, all designed to work out of the box with minimal measurements, saving you time and effort. Our toolset for characterizing noises has been discussed in a previous webinar where we used it to accurately characterize frequency noise via displaced cat states in a trapped ion experiment. For more details, see our publication in Physical Review Letters. We also have a suite of tools for characterizing errors at the algorithm or gate level. This work is best summarized in our recent manuscript, where we demonstrated improving the performance of quantum algorithms on a commercial quantum computer by a factor of over 1,000. This toolset will soon be available in our Boulder Opal scale-up package, which allows you to characterize quantum computers with over 50 qubits. Today, we will be focusing on our new results on characterizing the dynamics of a quantum computer. This approach to characterization is best used when you want to better understand the physics of your device, so you can design higher fidelity, more robust controls. A manuscript is available on the archive, which covers in detail all the results I will present today. You can find all Q-CTRL's technical manuscripts on our website, where they are free to download. Back to the focus of our presentation. In this slide, we show how Boulder Opal can characterize the dynamics of your quantum device in 3 easy steps. First, you define your best guess for the Hamiltonian of your system. We chose the Hamiltonian because it is the most common way to represent the dynamics of a device. Other representations, like master equations, can also work. As an example, we considered the Hamiltonian of a driven qubit. The first term consists of a guess for the Rabi rate multiplied by the control pulse. The control pulse will be automatically picked by Boulder Opal to gain the maximum information during the characterization process. You then have to provide a rough initial guess for the Rabi rate with whatever uncertainty you pick. In this case, we went for 10 megahertz plus or minus 20%. You can also add terms for potential noise sources. We include a detuning term, which can have a value between plus or minus 0.3 megahertz. Finally, you can set more complex terms in the Hamiltonian, which you wouldn't normally know how to characterize. Here we add a coherent coupling between the qubit and some ancillary qubit with a known frequency. Boulder Opal will automatically determine the optimal strategy to characterize all parameters in your Hamiltonian. All you have to do is input it. The next step is to run the experiment.
Boulder Opal will automatically create control pulses that extract the maximum information from the experiment. After each run, the measurement results must be fed back to Boulder Opal. It uses this information to update its estimate of the Hamiltonian and determine the next control pulse to use. This loop is repeated until Boulder Opal is able to find the true parameters up to the precision specified by the user. Once the experiment is complete, Boulder Opal will return the true Hamiltonian. It provides the values of all the parameters in the Hamiltonian you specified with an estimate of the precision. In this example, the algorithm was able to identify the true value of the Rabi rate of 9.551 plus or minus 0.005. This characterization process is completed automatically and is optimal, meaning the number of measurements is the minimum possible. Reducing the number of measurements saves you time and resources. So how does Boulder Opal do this optimal characterization? Well, the exact details are a bit advanced. So for those who really want to know, I'd recommend you read our manuscript where we go into more detail. Today, I'll just briefly mention that at the heart of Boulder Opal is a new algorithm we call USyd, which stands for Optimal Bayesian System Identification. We create a probabilistic model for the possible values of the parameters of the Hamiltonian. We then update this model after every measurement using Bayes' rule. This part of the algorithm is pretty standard. The real magic is how we pick the control pulses. The USyd algorithm finds the next control pulse by solving a complex optimization problem where it does a simulation of every possible future measurement outcome and then determines the pulse such that the average uncertainty in the parameters in the next step is minimized. This is equivalent to saying it optimizes the control pulse to ensure the maximum amount of information can be gained from the experiment. This slide shows an example of this optimization problem. Here we have the measured outcome plotted against two different parameter values for three different pulse lengths. The purple dot is our guess for the parameter values, with the white circle indicating the uncertainty. The best pulse length is the one where there is a unique value for the measurement outcome, shown in green, on the steepest hill. This results in getting a unique value for the parameter value with the largest reduction in uncertainty. In this case, the best option is the middle plot, so a pulse with a length of 2 is selected. Boulder Opal solves this optimization problem automatically, so you don't have to worry about it. This minimizes the number of experiments you have to run and maximizes the precision of the values you measure. If those last two slides are a bit complicated, don't worry. You don't have to know the details of how the algorithm works. We have designed Boulder Opal to be user-friendly, so all you need to know is these 3 steps to get it up and running on your device. Now we move on to the second part of this presentation, where we discuss our collaboration with the Quantum Control Laboratory at the University of Sydney. The QCL team are working on creating large chains of entangled trapped ions to push our understanding of physics and chemistry. Using these entangled ions, they are able to explore quantum chemistry by looking at analog simulations involving the motional states of the ions. They are also working on pushing our understanding of quantum control by examining the errors that are created when generating large chains of entangled ions. However, the team at QCL faces a challenge. Their control laser and imaging system does not address ions individually. This is preventing them from creating large chains of entangled ions. This challenge can potentially be solved using robust control. However, they need to accurately characterize their individual ions to do so. Characterizing ions with the standard approach is costly, requiring at least 300 measurements per run. Fortunately, Boulder Opal can solve this problem. We configured Boulder Opal to estimate the Rabi rate and detuning of one of the ions in the QCL experiment. We provided Boulder Opal with an initial guess for these values with a 10% uncertainty. The Boulder Opal algorithm was then run on a real experiment. It was able to converge the true values for the ions Rabi rate and detuning with only 5 measurements. This is an improvement by a factor of 60 when compared to the standard approach. Furthermore, the precision of the measured parameters was 1.55 times more precise than the standard method. We can combine these factors to get a factor of 93 times improvement in efficiency when comparing Boulder Opal to standard characterization techniques. So how did Boulder Opal get this huge improvement? Again, the answer lies in the USyd algorithm. Here we show the control pulses that were picked after each iteration of the experiment. We can see the USyd algorithm has perfectly picked the right pulse at every step to gain the maximum amount of information. It changes the pulse shape to better estimate the Rabi rate or detuning, depending on which one is more uncertain. It also increases the pulse length after each step to make its estimate more and more precise. We can more clearly see this trend of how the uncertainty and duration of the pulse are connected by plotting them as a function of the iteration, as shown here on a logarithmic scale. We can see the error and uncertainty of the parameter estimates reduces exponentially after each iteration. Correspondingly, we see the pulse duration increases exponentially with each step. This is the optimal scaling of accuracy when estimating a parameter from a qubit. This optimal scaling ensures that you get the right answer precisely with the minimum number of measurements. The next experiment we will complete with QCL is to run this characterization technique with a chain of ions. Once we characterize the Rabi rate and detuning of every ion in the chain using a common control laser and imaging system, we will be able to create optimized pulses to individually address each of the ions using Boulder Opal. This individual addressability will then be leveraged to create a highly entangled chain of trapped ions. The USyd algorithm presented today works on any quantum device, not just trapped ions. We have also completed simulations that demonstrate USyd can estimate the Rabi rates, detunings, and coupling strength of two superconducting qubits. Hopefully this presentation has given you ideas of how Boulder Opal's new characterization feature can be used on your quantum device. To get started, scan the QR code on your screen or contact our sales team by email. We would love to hear from you and discuss how Boulder Opal can save you time and resources by making quantum control easy.
So welcome back, everybody. Apologies for those technical issues. That was a bit of a callback to the very first webinar we ever did, where we had a fire alarm going off in the middle of the video. But I think I remember that. Yes. So for any of you who've been here from the beginning, hopefully enjoyed that little Easter egg. But back to the presentation at hand. So this is the Q&A section where we can answer any of the questions you may have about that presentation, the work going on at QCL, or anything else that Q-Control does. So if you have a question, please just click on that Q&A box and submit it. So thank you for the comments. That was such an iconic webinar. I appreciate it. I think the first question I just want to ask you, Chris, is so what was it like implementing the control solution in the lab? And I know we were talking about this before. You mentioned its robustness and some of the learning experiences we went through.
So maybe we can first comment on the robustness aspect.
Yeah.
So implementing in the lab, the first thing we have to do is correctly model our Hamiltonian. And the Hamiltonian we were doing was a kind of test bed. So that part was all right. And then the next step was tuning some hyperparameters. And after tuning that down, running the algorithm was quite robust. And when I say robust, I mean it would converge towards the correct answer almost all the time. Yeah. So that took an initial bit of tweaking of hyperparameters, but once that was fine-tuned for our specific Hamiltonian problem, then it worked very robustly.
Yeah. Yeah, and I think that's going forward. If we normally have to tweak this. Basically, there is this probability distribution inside it, and we have to normally tweak the number of samples we take, but that's very problem dependent. So you wouldn't need to do that for any other single qubit device. I think we've got that covered now. It's just if you have a new machine that you're trying it on, you would work with us to just get those settings right to ensure it converges every time. Yeah, yeah. So we have another question is, could this characterization technique be used on photonic qubits? Well, you guys work with lasers as well. Do you have any opinion about that? Do you think it could be extended?
I think it was mentioned in the slide towards the end that if you can write down a Hamiltonian for it, then in theory, yes. So if you can write down a faithful Hamiltonian, that accurately represents your system. And there's a term in that Hamiltonian that you would like to measure and characterize, then the answer is yes. I think it comes down to how faithfully you can model your system.
Yeah, exactly. That's the key take home is, yeah, it really can do anything. It's just you have to have a Hamiltonian that captures the dynamics of whatever you're looking at. So photonic systems are definitely a good possibility. I think I'll take this next one. So the question is, can fire opal and boulder opal be used together? So the easy answer to that is that they're two different products which have slightly different uses. So if you have a quantum computer set up and you want to get the absolute best performance from it, Fire Opal or our embedded solution, if you're a hardware developer, that's really your best bet because we'll be able to get in there and get the absolute maximum performance. Boulder Opal is really suited to people as basically your R&D teams. So your teams which are developing new chips or new devices, it's a complete package which allows them to characterize the device, try out new controls, and also do scalable techniques for characterizing the performance of the whole device quickly and rapidly. So it's really, I think they kind of complement each other and have slightly different purposes depending on your current state and your hardware predation. So next question we have is, what if the Hamiltonian the user inputs does not represent the actual system? For example, there is a defect two-level system coupled to the system and it throws off the dynamics. Would the optimized parameters be robust to this? Yeah, so I think you can kind of answer this because we initially tried the wrong Hamiltonian and what happened?
So we had at the beginning a bit of an issue that all came down to the hardware we're using, if that's what you're getting to. So we had various different ways to generate our control pulses. And one of those ways introduced these very small lags, these delays between two subsequent pulses. So when we were testing out control solutions with various different segments, there's some finite time between those segments where nothing was being played. And although that was extremely small, when we started pushing the limits of SID and started pushing limits to very long durations, then it started having an effect. So what we saw on the actual results is that our uncertainties would reduce and our estimated parameter would converge towards the right answer up to a certain duration at which these tiny imperfections started having an effect.
Yeah. So, and that is the challenge, but so basically to double down on that, it's because we were pushing the precision so hard, it kind of basically showed us that there was something we were missing. And the other good aspect of the technique is it can detect. So if you do give it the wrong Hamiltonian, because it has this statistical model, it can compare what results it's getting from the machine and compare them to what you provided it. And if it thinks that it's impossible for it to match them, it will actually show that up. So and that's why we were able to figure this out, because we were working with the team, we were looking at the data, and the algorithm was telling us, hey, the model doesn't fit the data you're giving me. You've got to review the Hamiltonian. So it's kind of goes both ways. You do have to come up with a Hamiltonian which covers the physics of the device. But the nice thing is the technique will detect and let you know if you need to put some more work into figuring out what's missing from your Hamiltonian. Next question we have is, how do you choose the control pulses and how do you shape them towards the quantum system? So what is the run experiment block about? Please give more details. So the part I'll answer is that the control pulses are actually completely selected automatically by the algorithm itself. So it designs the pulses themselves. For the particular experiment we did, we created piecewise constant pulses. And maybe do you want to tell them a little bit about how they were implemented on the device to actually drive that?
Yeah, sure. Yeah. So piecewise constant functions are multiple segments of some constant value. And what we told the protocol, what we told the optimizer is we want this many segments. And that's the baseline. And then within each segment, it will optimize a value. It will optimize a Rabi frequency and it will optimize a phase. And then what we did is in our particular experiment, we take this list of values and we feed it into our control system. And then there's our own code that then creates the pulses and sends it to the experiment. We did it in a way where we abstracted the system and then integrated that within the protocol. So the protocol would send a list of pulses to the system, and then the system would run it in an abstract way and then return a final answer. Now it is interesting though that we played around with different constraints on the pulses. So in the paper, and I think in the slides, you'll see that we had 5 segments. We also played with 3 segments, for example. And these pulses are very are arbitrary. There's no bounds. And then we started playing around with different constraints. So for example, we said that the phase can't change, and we can only change the amplitude. And the amplitude can change from -1 to 1. Then we also played around with other constraints where we said the amplitude is now constrained to 1 or 0. And these cases are particularly well applied to cases where you have Stark shifts, for example, where if you start applying pulses with different amplitudes, then you get different Stark shifts, and that starts messing with the faithfulness of your model. So the point I'm trying to make is we were playing around with different constraints and limitations on the pulses, and they all worked very well. They're all very robust, and this demonstrates the flexibility. And this flexibility is what attracts us the most about this.
Yeah. We have some increasingly technical questions, so I'll try and answer them as best I can. We'll probably go for another 10 minutes at most, so we're heading towards the last few questions. So the next one is, can you comment on how Boulder Opal manages things beyond Hamiltonian dynamics like open systems? So Boulder Opal is a very flexible framework, and it can handle simulation of open systems quite easily. It can also take into account, we're looking at features now to add stochastic trajectories as well. So this feature can be used with open systems. The only challenge is when you have an open system, the computation time, the wall time for the actual processing of the simulations themselves takes more time. So what we're currently doing, and one of the reasons that we're having this webinar, is to talk with people more about the specific cases they're interested in. So because once we understand what people want to use this for, we can really optimize the numerical code and get it performing at its absolute best. So if you have a particular open system you'd love to try it on, we would love to hear from you. The next is about the optimization of most utility functions in Bayesian experimental design are difficult since functions are multimodal with local optima. How was optimization performed, and which utility function was used? The Kullback Liebler divergence. So unfortunately, I don't have the actual specific term off the top of my head for which we used the actual optimization. That is in the paper. So if you go to the technical manuscripts, like all the details are in there. I will say that, yeah, indeed, it is quite difficult because you can have these multimodal features. But the key thing that we really did is by changing the control function, you notice that we optimized and we would perfectly pick the pulses such that in the area of uncertainty for the parameters that we're currently estimating, we only have one area or one line of the values of the parameters which can be measured on the next experiment. So by carefully picking your pulse shapes, you can actually ensure that you're searching in a region where you have a unique solution for the value, and then you can adjust that pulse to also increase the slope, not too far, but just far enough that you also make sure that you decrease your uncertainty in the parameter in the next result. But it is a difficult optimization problem. We use a particle filter to approximate it. And what you find is that if you don't have enough particles in your particle filter, then you can get issues where you don't converge. But in the cases we did on this experiment, and we're confident for the systems of like similar size, we were able to successfully get it converging robustly with around 5,000 samples of that particle filter. But that needs to be adjusted depending on your problem. So next question is, we've got a few. So maybe I'll ask this one to you next. So can the technique be used for characterization beyond single qubits?
Well, the short answer is yes, in theory.
Uh-huh.
again, if you can model the Hamiltonian faithfully, there's no reason why the protocol itself shouldn't work. Obviously, if you go to 1,000 qubits, then you start running into computational issues. It's not clear yet where the limit is. Maybe you can comment more.
Yeah, I'd say the limit is purely amount of like optimization on our end. So what we're currently looking to do a 3 qubit. That's probably our next step. We're trying to do 3 qubits with this common beam that we talked about before. And beyond that, there are a variety of different techniques we can use to optimize the numerical apparatus and make it go faster. But would love to hear from you guys what you're interested in applying it to, so we can really target those applications. Yeah. Next question is, how is the Boulder-Obel algorithm configured to achieve optimal exponential scaling in the presence of noise? So in particular, if the noise is non-Markovian and can result in shot-to-shot variations that are often present, for example, with magnetic field sensitive qubits. That is a very good question. So the particular example we considered today was when you may have a noise, but that noise is fixed over the time scale that you do the measurements. So some non-Markovian noise processes, like thermal drifts, are actually relatively slow. And so you may be able to estimate them as if they're approximately constant during the characterization scheme. Once you have a noise process which is faster than the total duration of the experiments you're doing, so you're bringing it into that really challenging medium area. The first thing is there are other tools in Boulder-Obel which are better designed to characterize non-Markovian processes, but we're also looking at extending this tool to be able to estimate non-Markovian processes which are parameterized by the user. And indeed, when you're in that scenario where you have these noise processes, you won't necessarily be able to achieve the same scaling that we did. So the scaling that we did, we do see consistently on most superconducting devices when you're like trying to if you're trying to accurately increase your precision on the fidelity of that gate, or otherwise the tricks that we use today are basically extending or repeating your gates, work just as well. But there are really challenging cases sometimes when that noise process is changing on a medium time scale. And that's something which we're still considering and looking at further developing. Next one is the piecewise constant control pulses, where the duration and the amplitude of each segment are the optimization parameters. Did you also consider changing the drive frequencies?
For this particular work, we didn't change the drive frequency. Is that possible?
Yeah, I guess that's it is possible. So we just we just didn't do it because I think
I don't think it would have gained us much. I don't think it would have helped our particular case. So it is. You can just add it in Boulder-Obel.
Yeah. Next question. I'll cover the last few a bit quicker. So, what happens when the noise in your system makes parameters oscillate faster than one iterationary algorithm? So, yeah, I kind of addressed that in that previous question. So, but the key thing is, as long as you can parameterize it, we're confident you could start to take that into account, but it does indeed really change the nature of the estimation problem. And that's something that we're looking at now. So next quick question is, what other simulation techniques are available in the Boulder-Obel package? We have everything from adaptive time step algorithms to fixed exact time exponential series approaches. We have also a new feature coming up where you can solve for the steady state of open systems. Just go to the Boulder-Obel website and you can see the many simulation examples we have available. And with regard to there is, of course, a few different ones also for open systems. At the moment, the standard approach that's available is a deterministic approach where we solve the master equation directly, but we're looking to add features on stochastic optimization there as well. Here's a good example. So you mentioned that fewer experiments are needed using these optimal controls. What were the number of shots per experiment? I would assume that the number of shots would come into play with the likelihood model. Maybe. So what's the number of shots with the individual measurements?
So if I remember correctly, they were on the order of 50. It's in the paper, so don't quote me on that. It's either 50 or 100, but I think it was 50.
Yeah.
For the OBSID protocol. And more importantly, though, it was 6. Again, don't quote me on that. Either 5 or 6 iterations. And so in only 5 or 6 iterations with 50 to 100 shots per iteration, we were able to converge towards a good solution with very minimal uncertainty.
Yeah.
So that's opposed to, for example, doing a driven oscillation and then sampling many points of that driven oscillation, each with maybe the same number of shots. But to get the same number of accuracy, in that case, you would have to go for many more repetitions.
Yeah. And so we went with that approach because we could have fed individual projective measurements into the algorithm, but in practice on superconducting devices and in ions, it's relatively cheap to repeat an experiment a few times. And so running the particular measurement 50 times is a much more efficient way of getting you a better estimate of the mean and standard deviation. And then that allows for the algorithm to converge a lot quicker because you get a kind of clearer signal. So that's why we went with that approach. But in principle, you could also feed individual measurements. You just have to change the Bayesian model that you're using under the hood. So now that we're hitting the last minute, so I've got one more question. So for the run the experiment part, the user has to provide their own interface for the experiment. Is there any framework that's built into Boulder Opal, like Laba, QC, so QCodos? I'll just mention, so we've really designed Boulder Opal to be flexible with whatever you want to integrate it with. Do you want to maybe comment on how you specifically integrated it into your device? Yeah.
So the particular version of the protocol we had returned, we treated it as a black box, and it was just a function that we call, and it returns a list of values, and this is all in Python. And that list of values, we then just send it over through the network to our experiment. What happens on the experiment is maybe a bit more obscure, and that again also we treat it as a black box. So it really is just the protocol, which then spits out a list of controls that we then feed into our experiment. And then our experiment spits out a measurement value, which we feed back into the protocol. So all this was integrated in Python. And for us, it was just copy and paste in a function that we created, which interfaces with the experiment.
Yeah, and I think that's currently our philosophy, is that because it's all as long as your package is in the Python environment, it really is very, very easy to connect the two. But we have looked at specific integration packages for devices like quantum machines, and we're open to further integrations. It's just a matter of figuring out which ones are the most common for our partners. And we've just found that everyone kind of has a different flavor of the month at the moment. So normally what our main aim is just to make sure that Boulder Opal is well documented, clear, and integrated into that Python environment so you can use whatever you like. Great. So that ends our session. Thank you again, Chris, for joining us for our.
My pleasure. Thanks for having me.
It's been great to have you here. And this is going to be the first in our new series of webinars from Q-CTRL. So please sign up. And at the end of this, there's going to be a survey where you can tell us a bit about your experience of the webinar and what else you'd like to see in the future. And we'd really, really appreciate it if you fill that out. So thanks again, and see you soon.